my name is Stephen Arrett, and this is my video presentation on dependency injection in .NET. Today we're going to look at what dependency injection is, what the most common types are, and examples of each. Let's get into it. Let's start with some definitions. A dependency in software development refers to the relationship between two modules or components, where one module relies on the other to function properly. Dependency injection is a set of software design principles and patterns that enables you to develop loosely coupled code. It is the implementation of inversion of control, which is the broader concept of letting external systems or frameworks manage certain aspects, making the code more adaptable and efficient. Loosely coupled code refers to a design principle in software development where the parts of the system are relatively independent of each other. In a loosely coupled system, a change to one component does not have a significant impact on any other components. Each module is designed to operate independently, with minimal dependencies on other modules. Tightly coupled code refers to a situation in software development where components or modules are highly dependent on each other. In this scenario, you can't change one component without affecting one or several other components. This requires all dependent modules to be changed at the same time in order to function correctly. Developers should strive to make their code loosely coupled in order to enhance flexibility, simplify maintenance, and promote scalability within their software systems. So, what makes dependency injection useful? Software requirements are subject to change, whether due to evolving business needs, user feedback, or external factors. Dependency injection, or DI for short, brings flexible and maintainable code to software development. Modularity is one of the main goals for DI. Dependency injection helps decouple components by externalizing the dependencies between them. This means that one component does not rely on the internal details of another. This loose coupling enhances flexibility, making it easier to modify or replace components without affecting the rest of the system. DI also helps with testing. With dependency injection, it becomes easier to test components in isolation. By injecting mock or test-specific dependencies, developers can focus on testing the behavior of the individual components without the need for complex setups. This contributes to the maintainability of the codebase by identifying and resolving issues through effective testing. DI can make scaling easier. As a codebase grows, maintaining a clear and understandable structure becomes crucial. Dependency injection promotes a modular and scalable architecture. New features or changes can be introduced without tightly coupling different parts of the system, making it easier to extend the application's functionality. DI also lets systems adapt. DI allows for more dynamic configuration of dependencies. This means that changes in requirements or business logic can be accommodated by adjusting the injected dependencies rather than modifying the internals of the existing components. This adaptability is essential in modern software development where change is frequent. Dependency injection often leads to code that is easier to understand. When dependencies are explicitly declared and injected, it's clear what a component relies on to function. This transparency aids in the maintenance of the codebase, as developers can quickly comprehend the structure and relationships between components. The three main types of dependency injections are constructor, setter, and method injections. In a constructor injection, dependencies are injected through the class constructor. This is the most common type of dependency injection. It ensures that a class cannot be instantiated without providing its required dependencies. In setter or property injection, dependencies are injected through setter methods. The class provides setter methods for each dependency, and the client can set these dependencies after creating an instance. It allows for more flexibility, but the class might be in an incomplete state until all dependencies are set. In method injection, dependencies are injected through methods. Dependencies are passed as parameters to specific methods that need them. This is useful when certain methods require different sets of dependencies. Now imagine a car and its engine. A car needs an engine to run, and the engine is responsible for starting the car. Dependency injection is like giving the car its engine from the outside. Instead of the car deciding what kind of engine it needs, we provide the engine to the car. The following is an example of constructor injection, where the dependency, the engine, is injected into the class at the time of its creation. You can pause the video during this example to review the code snippets in detail. This is an interface named iEngine that declares a method start. An interface is like a contract that defines what methods a class implementing the interface must have. In this case, any class that implements iEngine must provide a method called start. Different types of engines can be injected into the car without changing how the car works. Here we have two engine classes that implement the iEngine interface. The car class needs an engine to start. We will use dependency injection to provide the engine during the car's creation. Dependency injection, in simple terms, is like providing the car with the engine it needs, enabling us to easily swap different engines without changing the car itself. By injecting the engine interface, iEngine, into the car class, we make it straightforward to switch between different types of engines without modifying the car class. The output of this code will be the string starting gasoline engine, since that's what the gasoline engine start method dictates. This showcases the flexibility and modularity provided by dependency injection. In setter injection, we enhance the flexibility of our car class. In the class, we declare a public property named engine with a capital E. This property has a set accessor, indicating that external code can set the value of this property even after the car object is instantiated. The start method checks if an engine is set before attempting to start the car. It gives an error message if no engine is found. This dynamic approach allows us to adapt the car's behavior on the fly. Method injection introduces a different dynamic in our car class. The start method now accepts an iEngine parameter, allowing external code to inject different engines when starting the car. This versatility enables us to tailor the car's behavior for specific scenarios. For instance, external code can inject an electric engine for a silent electric start, or a gasoline engine to initiate a more powerful combustion-based start. This level of fine-tuned control over the starting process showcases the power of method injection. In conclusion, dependency injection, DI, proves to be a key player in the world of .NET development, bringing flexibility, modularity, and adaptability to the forefront. This coding technique, rooted in loose coupling, stands as a practical solution for handling evolving business needs, facilitating effective testing, and ensuring scalability. By externalizing dependencies, DI fosters code maintainability, making it easier to comprehend, test, and modify. There's a lot more to DI than is covered in this presentation. If you want to know more, you can view my references at the end of this video and in the description.